Okay, so welcome back to Truth Seekers Club, everybody. And uh, today I will be presenting the second lesson. Before I begin, I want to make mention, though, of a few items from our last lecture, the lecture from last week. And the first thing that is important to remember is that in order for Truth Seekers Club to be valuable to you, you must desire to want to engage with people concerning the reality that there is a God and also that Jesus really is his son and the way of salvation. That's got to be in our hearts. This is the most important thing about our lives, and so it must be our prayer at all times that God will give us a chance to have a meaningful conversation with somebody about God. And it's funny, when you pray that prayer, God does give you chances, but you have to want it. You have to say, God, give me that. I really want that. Our hope is that they will believe. We want people to come to faith in Christ, but even if they don't, we at least want to be able to move them along a little bit in the journey of thinking about, is God really true? And move them a little closer to understanding the truthfulness that Jesus is the Son of God and the Savior, the one who is able to forgive sins and make it possible for us to go to heaven. So one of my favorite methods, I thought I would just quickly give you a review here. When I meet somebody new, before I talk to them very long at all, because the thing is, the longer you wait, the harder it gets to bring up the subject of God. At least I think so. So early on in the conversation, I want to say something like, hey, do you believe in God? Because if you start off quickly and just kind of bring up the God subject, they don't think it's that strange, or they might think it's strange, but it's less strange than if you wait too long. But just say, do you believe in God? Or are you a person who believes in God? And from there, as we know, the conversation can go in a million ways. If you just say, hey, are you a person who believes in God? There's all kinds of things that can happen. But it's a good way to get the conversation started. So then if they say no, which a lot of people do not say no, especially in America. Even though they, practically speaking, they are living as if they did not believe in God, which is a different problem. But if they do say no, I don't believe in God, then the next question that I want to ask them with genuine respect for their answer, because you do want to respect, that's the whole thing. We're treating people like they're people, because they are people. We want to really show them proper respect. So I want to say to them, when you think about it, if you don't believe in God, what would you say is the number one reason that you don't believe in God? That's really a respectful question to ask, because you're just saying, I'm just curious. I just want to know, what do you think is the number one reason why there's no God? So I want to ask that. You're really genuinely interested in their story. And of course, you demonstrate that by listening to their answer and asking them more questions. But if they say that the number one reason that they don't believe in God is science, then this is a place where you might get to share some of the things of what we're talking about, when it's appropriate. And you might want to say something like, it's so funny that you would say that, because I actually came to the opposite conclusion. It was science that strengthened my faith in God. Now, if you get to that point in a conversation, it really is good that there's something in your heart that really does excite you about science that points you to God. So it's nice to have things that you can say, but I'm just kind of showing you how it works when you lead into a topic about God, a conversation about God. So it's nice to have an example ready to share, like something you can just say in a few sentences. So you could say something like, one of the things that I'm learning about right now is how recent scientific discoveries seem to be pointing to the existence of God, specifically the fine-tuning of the earth and the universe. You know, at one time, it was common thinking in the scientific community that probably advanced life existed in many places throughout our galaxy and universe. But in recent years, very recent years, scientists, from what they are learning, the data suggests that the conditions that are needed for life to exist on a planet or even in the universe at all are so numerous, and each of them so carefully fine-tuned, that it does not seem possible that it could have happened by chance, that life could have come about by chance. I'm just kind of giving you an example of how you might lead into it. And then you could say, think about the force of gravity. Think about the force of gravity. The force of gravity has to be exactly what it is, or life could not exist. You know what gravity is, right? So we can just say something like that. Do you know that the force of gravity has to be exactly what it is, or we would not exist? It's so carefully fine-tuned. Now, I'm going to stop right there with the hypothetical conversation, because I think you get the picture of how the things that I'm presenting to you can work in a conversation. But I do not want to I don't want these to be boring facts to you, like just facts that you have to memorize. Rather, it's important that you yourself have a sense of excitement and genuine wonder about these things. Therefore, I want to give you two quick history lessons, which I think you'll find interesting, so that you can see how the story has been unfolding, and you'll also see the significance of the facts that have recently been coming out through science. So I do want to talk about gravity today because it is such a basic prerequisite for life. Now, Isaac Newton, did you know who discovered gravity? Isaac Newton lived in England, and he's the person who discovered gravity. And do you know what year he discovered it? The year 1666. So just about 300 years before I was born. In fact, when I was 2 years old, I celebrated the 300th anniversary of the discovery of gravity. In other words, it wasn't that long ago, relatively speaking, right? Only 300 years ago. They didn't know what gravity was 300 years, 350 years ago. All right, so as you know, at least the story goes like this. Isaac Newton was thinking about the laws of nature when he witnessed an apple, right? Have you heard this before? An apple falling from the tree. And that really started him wondering, and it also led him to start doing some experiments, like shooting a cannonball off of a mountain to see if it did what he thought it would do, and the trajectory, and etc. Now, before the discovery of gravity, it was just assumed that when you looked at the moon going around the earth, or for that matter, any movements that you saw in the heavens, it was assumed, before 1666, it was assumed that it was just God that was doing it. He's holding them there. Or if you didn't know the God of the Bible, you just thought it was one of the Greek gods or Roman gods. But Isaac Newton realized, once he understood gravity, Isaac Newton realized that the implications of gravity, that if there was no gravity, the moon would fly off from the earth. But because of the existence of gravity, the moon is really just a projectile that has been captured by the Earth's gravity, and therefore it keeps revolving around it. Therefore, now we know that even though gravity is the weakest of the four forces that exist in the universe, the four different forces that exist, gravity is the weakest of those four, yet it is the force that governs the movements of the planets and the stars and even the galaxies. That's gravity that's working out there. Everything. So the definition of gravity is the universal force of attraction acting between all matter. So whenever you have two things of matter, they are exerting gravity. And one thing I learned is that there's no end of gravity. Your gravity extends however small it may be, but it extends out through the whole universe. So gravity is there. It exists between all things. We could say it's the force of attraction that one body exerts upon another. So the bigger the body, the more force it exerts. For example, did you know that based on the discovery of gravity in 1666, that astronomers predicted the discovery of Neptune, planet Neptune. They knew about Neptune before they saw it. Because of what? Because of gravity. What happened was, when they looked at the orbit of Uranus, the planet Uranus, they could see that some force was causing fluctuations in the orbit of that planet. And sure enough, Neptune was discovered shortly after that, doing exactly the mischief that they had detected. Isn't that interesting? But here's the interesting thing. Gravity, listen to this, has a number. And I do have a slide of it. So, Toshiko, can we put up the slide of the gravitational constant? How does this work now? Oops. Okay. Now, this number is called the gravitational constant, and as you can see, all right. Trying to adjust my screen, but I cannot. It's not doing what I want it to do here. All right. So this number is called the gravitational constant, and as you can see, oh, this is not going to work. Oh, there we go. Okay, so here's the number, and I got this sentence from the website at Stanford University. The best current estimate of G is that it equals about 6.67259 to 10 to the minus 11 Newton square meters per square kilogram. Now, you guys probably already knew that, and I don't really even know what that means. But if you are an astronomer, this is like an everyday kind of number. Because you use it every day to calculate what the force is between two celestial bodies. For example, the force of gravity between the Earth and the Moon. So I made a slide of the formula that an astronomer would use, and here it is. Toshiko, if you can switch to the next slide. Okay, so this is the slide for calculating the force of gravity between two objects like the Earth and the Moon. So this is what the sentence says. In symbols, the magnitude of the attractive force, that is the letter F, represented by the letter F, is equal to G, and that's that number that I was telling you about, the gravitational constant, a number the size of which depends on the system of units used and which is a universal constant. It's multiplied by the product of the masses, so the mass of the Earth times the mass of the moon, and divided by the square of the distance, which is represented by the letter R. So now you have to remember, you don't have to remember all of this, but what you do need to remember is that the gravitational constant is a number that God finely tuned. He made it just so. 6.67259 times 10 to the minus 11. It's a very small number, but it has to be exactly that number for life to exist. Isn't that interesting? I mean, 6.67529 times 10 to the minus 11. It has to be that. In fact, if you remember the video that I showed you last week by Eric Metaxas called Does Science Point to God? He mentioned the 4 forces that exist in nature, and he said that if you alter them even by just a little bit, the universe could not exist at all. That was kind of the startling thing that Eric Metaxas said last week. And that shows the high degree of fine-tuning of the earth and the universe. You know, he said in that video, the odds of these numbers just so happening by chance to be what they are defies common sense. Right? I think that should create in us a sense of wonder. That should stir our hearts. It defies common sense. He said it's like flipping a coin and having it come up heads, not just 10 times in a row, but 10 quintillion times in a row. And then remember he said, I don't think so. It doesn't happen. You can't, it's just, the odds are just so astronomical. All right, so that's the first story about Sir Isaac Newton discovering gravity and just what a miraculous thing he discovered. Secondly, the second story has to do with another number, which is also exceedingly carefully balanced. And this one is called the cosmological constant. And I'm going to tell you the story behind it, because if you're like me, it's easier to remember a story than a number. Again, it's a number that has to be exactly right for life to exist and for the universe to exist at all. And this time it has to do with Albert Einstein, another name that's familiar to us. Albert Einstein published his theory. If you know when he lived, he published his theory of general relativity in what year? In the year 1915. All right, that's when Albert Einstein published his theory of general relativity, about 100 years ago. Now, Albert Einstein believed that the universe was static. All right, that means that he believed that it was not expanding or contracting. It was just floating. But when he did his calculations, according to his theory of general relativity, when he did his calculations, he noticed that based on the theory of general relativity, when he put the numbers in, then actually he discovered the universe should be expanding. What? It seems like, according to the numbers, the universe is expanding. Well, he thought that just can't be. In fact, he really didn't want it to be true, but he didn't believe it could be true because that would mean that the universe had a beginning. That's why scientists didn't really want to believe that the universe was expanding. Because if it had a beginning, then that also implies that it had a beginner. And there just was a notion among scientists that could not have happened, that the universe could not have had a beginning. No, 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 no. That must be wrong. It must have always been here. So he kind of didn't want it to be true. And so what he did was, when he made when he had the general theory of relativity, what he did was he added in a certain number in order that the calculations, when you worked them, would come out to show that the universe was static. It's not moving. All you have to do is add in this one number. It's called the cosmological constant, and that will balance everything out so that the universe is standing absolutely still. It's called the cosmological constant. However, here comes the monkey wrench. Another person who we recognize his name, this is Edwin Hubble, who I mentioned last week, who was an astronomer. He's the one who discovered, remember last week I told you he discovered that the Andromeda Nebula was actually what? The Andromeda Galaxy. You know, that was when we first learned that we were not the only galaxy. Well, it was this same Edwin Hubble who, based on his measurements, confirmed that the universe is not standing still, but it is expanding. All right? Edwin Hubble made that discovery, I think it's in 1924. So in the year 1931, Albert Einstein removed the number from his equation, and listen to this, he called it the single greatest blunder of his career because he overrided what the evidence and what science itself, what the numbers were telling him. He overrided it because he just did not think it could possibly be true that the universe is expanding. The funny thing, though, is that the number that he used turns out to be a very important number because what scientists have discovered is that if that number, that precise number, was a little bit bigger, the universe could not exist at all. Or if that number was a little bit smaller, the universe could not exist at all. It has to be exactly what that number is. You understand what I'm saying? So it's very finely tuned. Like of all the things that are finely tuned, this one is the most finely tuned of all. It's called the cosmological constant. It has to be what it is, and it cannot be changed even in the smallest degree. Now, again, I have a slide. I hope these aren't too boring for you, but this is a slide of this number, which is, again, it's not going to mean too much to you, but I'm just trying to show you that it exists. All right, so I got this from Wikipedia. The numerical value of the cosmological constant is calculated using a recently suggested cosmological model and found to be so that's the Greek letter lambda. Lambda, which is the symbol that's used for the cosmological constant, lambda is the symbol that they use. So lambda equals 2.036 times 10 to the minus 35 times s to the minus 2. So this value of lambda is in excellent agreement with the measurements recently obtained by the High Z supernova team and the Supernova Cosmology Project. Now, again, I don't expect you to understand that. I know I don't understand it. But the key thing to understand here is that only in recent years, I mean, Edwin Hubble, was 1924. Only in recent years do we have the science that's able to show us the kind of razor edge accuracy with which our universe is balanced in order for life to exist. Now, one of my favorite apologists is William Lane Craig, and he has a website called Reasonable Faith, which is a nice one to go to if you want to, Reasonable Faith. What I love about him is that he's very good at presenting powerful arguments for the reasonableness of the Christian faith. And what I want to do now is show you a video that his ministry put out, which is called The Fine-Tuning of the Universe. And this video is about 6.5 minutes long, but it is so worth your time because it uses pictures to see just how amazing it is that the universe has been so finely tuned, especially when it comes to gravity and also the cosmological constant, plus other specific numbers that there are in the universe. So please listen carefully and enjoy this powerful video, which is a good summary of what I have just been talking about.
From galaxies and stars, down to atoms and subatomic particles, the very structure of our universe is determined by these numbers. These are the fundamental constants and quantities of the universe. Scientists have come to the shocking realization that each of these numbers has been carefully dialed to an astonishingly precise value, a value that falls within an exceedingly narrow, life-permitting range. If any one of these numbers were altered by even a hair's breadth, no physical, interactive life of any kind could exist anywhere. There'd be no...
Just having a little bit of technical difficulty. Just this is what I always say, just bear with us. We'll get it figured out. Yeah, Carol. Yeah, so two of them have to do with the force inside of atoms. One is called the strong nuclear force, and one is called the weak nuclear force. And the other one is called the electromagnetic force. So those are the four, and they are very carefully determined. They know exactly what those numbers are, and they have to be exactly right, or atoms don't exist. Like matter can't exist because those numbers are very carefully, finely tuned. That's a good question. Let's try one more. Was it muted? Okay.
From galaxies and stars, down to atoms and subatomic particles, the very structure of our universe is determined by these numbers. These are the fundamental constants and quantities of the universe. Scientists have come to the shocking realization that each of these numbers has been carefully dialed to an astonishingly precise value, a value that falls within an exceedingly narrow, life-permitting range. If any one of these numbers were altered by even a hair's breadth, no physical, interactive life of any kind could exist anywhere. There'd be no stars, no life, no planets, no chemistry. Consider gravity, for example. The force of gravity is determined by the gravitational constant. If this constant varied by just 1 in 10 to the 60th parts, none of us would exist. To understand how exceedingly narrow this life-permitting range is, imagine a dial divided into 10 to the 60th increments. To get a handle on how many tiny points on the dial this is, compare it to the number of cells in your body, or the number of seconds that have ticked by since time began. If the gravitational constant had been out of tune by just one of these infinitesimally small increments, the universe would either have expanded and thinned out so rapidly that no stars could form and life couldn't exist, or it would have collapsed back on itself with the same result: no stars, no planets, and no life. Or consider the expansion rate of the universe. This is driven by the cosmological constant. A change in its value by a mere 1 part in 10 to the 120th parts would cause the universe to expand too rapidly or too slowly. In either case, the universe would again be life prohibiting. Or another example of fine-tuning. If the mass and energy of the early universe were not evenly distributed to an incomprehensible precision of 1 part in 10 to the 10 to the 123rd, the universe would be hostile to life of any kind. The fact is, our universe permits physical, interactive life only because these, and many other numbers, have been independently and exquisitely balanced on a razor's edge. Wherever physicists look, they see examples of fine-tuning. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. If anyone claims not to be surprised by the special features that the universe has, he's hiding his head in the sand. These special features are surprising and unlikely. What is the best explanation for this astounding phenomenon? There are 3 live options. The fine-tuning of the universe is due to either physical necessity, chance, or design. Which of these options is the most plausible? According to this alternative, the universe must be life-permitting. The precise values of these constants and quantities could not be otherwise. But is this plausible? Is a life-prohibiting universe impossible? Far from it. It's not only possible, it's far more likely than a life-permitting universe. The constants and quantities are not determined by the laws of nature. There's no reason or evidence to suggest that fine-tuning is necessary. How about chance? Did we just get really lucky? No. The probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe, inhabited by billions of other observers. So even if the multiverse existed, which is a moot point, it wouldn't do anything to explain the fine-tuning. Given the implausibility of physical necessity or chance, the best explanation for why the universe is fine-tuned for life may very well be it was designed that way. A common-sense interpretation of the facts suggests that a super-intellect monkeyed with physics, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. There is for me powerful evidence that there is something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge.
You know, when I watch this video and I get to that part where the words on the screen ask the question, why is the universe fine-tuned for life? Like, Why? And then the narrator says the best explanation for why the universe is fine-tuned for life may very well be, quote, it was designed that way. And then on the screen you see those heart-stoppingly beautiful images of the universe. Folks, my heart is so stirred. I think it should be. When we think of the implications of this, that I mean, those are not Christians. Those are just scientists. In fact, those are great scientists. Those are the scientists that people know by name. And that's their quotes. That it's beyond comprehension why these numbers are so carefully fine-tuned. What a wonder it is that we live in a universe that God himself has so dramatically and carefully designed and then given us the ability to discover it. I mean, to detect it and to find it out for ourselves. You know, this is not just the conclusion of born-again followers of Jesus Christ. Scientists themselves are saying it is very surprising, these numbers that they are discovering. They're being blown away by the inescapable conclusion that the numbers are pointing to, which is, it seems to have been designed. All right, I probably have spent too much time on this already, but I want to show one more video by Frank Turek, and he's not my favorite apologist, but he brings up a good point in this one, which he points out that these numbers are not the way they are because they evolved that way. You know, God put them in place at the beginning. So this is just 1 minute long, so watch this short video from Frank Turek.
Life. In fact, let's start with an atheist, Stephen Hawking. He put it this way. He said, if the expansion rate of the universe was different by 1 part in 1,000 million, a second after the Big Bang, the universe would have collapsed back on itself or never developed galaxies. In other words, if the expansion rate was that infinitesimally different from the very initial creation point, none of us would be here. Now, you can't make any evolutionary argument for this. You can't say the expansion rate evolved by chance to the right rate. Why? Because this is an initial condition of the universe. This is how it started. It didn't evolve, it just started that way. It seems to me the same being that created space, matter, and time is the same being that fine-tuned the expansion rate to be precisely what it needed to be.
He just kind of says it like it is, but that's the truth. The scientists say that those numbers were established like I forget, like a millionth of a second after the Big Bang. That's what their independent numbers say. That was an initial condition from the very beginning. It did not evolve to be that way. So it really is important to understand that these laws and constants which govern the universe could have been any value. And this is what's so surprising to scientists. There's no reason why they had to be set at any particular value, but it just so happens that they are set to exactly the right spot, to the right degree, in order that life may exist and the universe may exist. Therefore, it's extremely hard to say, well, I suppose we were just lucky. It's very hard to say that. Now, the world wants to say that, but if you hear that, you should say, I don't have enough faith to believe in that kind of luck, because that's really what they're saying, that there could be that kind of luck, that these numbers could be just exactly what they happen to be. The evidence suggests that it was designed. God finely tuned the value of gravity and the cosmological constant and the electromagnetic force and the weak and strong nuclear force, etc., 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 all for the benefit of, guess who? Human beings who were created in his image, which the Bible has said from the beginning. Folks, does that not stir your heart? I mean, I love thinking about this. The massive complexity and intricacy that goes into it, creating a universe and a galaxy and a solar system and a world, just so me and you, who are made in the image of God, can live out our lives giving glory to him. Now, with the time that I have left, oh boy, I want to return to talking about the fine-tuning conditions that are needed for life to exist, and specifically just how rare planet Earth is, as the scientists are beginning to discover. Now, if you remember from last week, I mentioned to you, it's important to remember that this is a cumulative argument. Now, the cosmological constant, you don't need to add too much else to it because it's just a blow you away kind of number. But when we look at the fine-tuning of the Earth, it's more of a cumulative argument, which means that there are lots of little factors that are necessary for life to exist on planet Earth. And the big problem is that you don't need just one or two of them to exist. You have to have all of these little factors at the same time. They all have to be right. So you have a whole bunch of little factors, but they all have to be right at the same time. And so when you add all that up, then you see the fine-tuning of planet Earth for life. So last week I shared with you a number of the parameters that have to exist in order for a planet to be suitable for life to exist. And at this point, I am just going to mention a few of them again. Except that I am not going to do it myself. I am going to let Jay Richards do it. He is the vice president of the Discovery Institute in Seattle, Washington. He graduated from our own Princeton Seminary right here in New Jersey, and he has a PhD. And he's the co-author of the book that I mentioned last week called The Privileged Planet. He co-authored it with an astronomer named Guillermo Gonzalez. And interestingly, his PhD is in philosophy. He's considered a scientific philosopher, and he is an excellent speaker. And I'm going to let him remind you of 10 of the factors. There's many more than this, but just 10 of the factors that have to be right in order for life to exist on any given planet. And so I'm just going to say that he begins by talking about how important it is to have water on the planet, which is probably one that you would guess right off the top of your head. So with no further ado, here is Dr. Jay Richards, and it takes about 4.5 minutes to watch this video.
That's the one need you're going to have. The other thing is you're going to need a matrix where these chemical reactions can take place. Well, it just so happens that carbon chemistry is most reactive over the same narrow range of temperatures over which water is liquid. All right, so think of the range of possible temperatures in the universe from, intergalactic space near absolute zero to the surface of stars. There's only, 100 degrees Celsius where water is liquid, and there's one element that's most reactive over that same range. So what that means is that liquid water and carbon chemistry fit like a hand in glove for life. And so this is why we don't waste our time looking for life on the sun. We send probes to Mars because we know you gotta have water. And so it doesn't mean that if you have water, it's just add water and you get life. It's that you need at least water in order to have life. Now, why does this matter? It matters because what this means is we can already rule out, even in a universe that is exquisitely fine-tuned for life, a very big universe in which a lot of stuff can take place, most of the places are not going to be compatible with life. So already by itself, we know that Earth is going to be a very unusual place. And everything we've learned in astrobiology, and my co-author Guillermo Gonzalez is the expert in this, I'm just summarizing it, have led to the conclusion as we learn more and more that the list of ingredients you need to build a so-called habitable planet just gets longer and longer and longer and more complex. Again, this is a kind of cartoonishly simple idea here, but what kind of things do you need? As I mentioned, you need liquid water. And you don't just need water sort of floating in interstellar space. You need the right kind of planet. You need a surface for that water and a surface for life. And not just any old kind of planet. You need a so-called terrestrial planet, which that actually means Earth-like. But think of it as a rocky planet with a surface. The planet needs to be the right size. Too small, it won't be able to hold things and like an atmosphere on its surface. Too large, and you end up with something like Jupiter or Saturn with way too much hydrogen and things like that. So it needs to be the right size. It needs to be made up of the right kinds of things. Something like a liquid iron core like we have that creates a magnetic field around the surface of the planet which protects life and the atmosphere. Turns out you need a large stabilizing moon like ours. The moon, it turns out, if we were to blow up the moon, over several thousand years, the Earth would start wobbling erratically on its axis. It'd also mess up the tides. So we didn't know this, but if the moon were not in our sky, we probably would not be here because Earth would not probably be compatible, at least with large animal life. You need plate tectonics that keeps the kind of long-range cycles of carbon up on the surface and keeps the stuff that life needs up near the surface. You need the right kind of atmosphere, probably a nitrogen and oxygen-rich atmosphere. Again, I'm just gliding over this, but when you get carbon chemistry, there's some kinds of atmospheres that work and some that won't. You need the right kind of planetary neighbors, believe it or not. Astrologers always believed that the planets played some role in our existence. I think they're wrong in general, but they were right, at least in this sense, that if we didn't have large outer-lying planets in our solar system like Jupiter and Saturn, the inner part of the solar system would be visited by far more comets from the outer part of the solar system. But because of these giant planets in the outer solar system, they think of them as sentinels that protect our neighborhood of the solar system from too many bombarding comets. Comets are sort of like your crazy aunt. You don't want them visiting so often, just every so often. And unlike your aunt, their problem is they can vaporize life on a planet. So it's like, please don't visit very often. And so, actually something like an arrangement of the solar system we have is actually really important for the habitability of Earth. Even though those other planets aren't habitable, they play a role in making the Earth habitable. Then you need to be around the right kind of star, the right size, the right age. It needs to almost certainly be a single star. Most stars in our galaxy are either together, either triplet or binary stars. You need to be in the right galaxy, the right kind of galaxy. You need to be in the right place in the galaxy, the right galactic location. And you need to be at the right time in the history of the cosmos. Now, I'm not going to
All right, so what you notice is simply this. Each one of those things that he mentions does not really seem that remarkable on its own, like you could find it in multiple places in the universe. But when you start explaining that every single one of those things needs to be present at the same time, what happens is the odds get lower, right? It gets less and less likely that there's a whole bunch of places where advanced life could exist. That's why we call it a cumulative argument. The power of the argument is when you look at all the little things that are necessary for life to exist, and you need to have them all at the same time and at the same place. Now, one of the things that Jay Richards mentioned in that lecture was that you have to be in the right kind of galaxy. And I don't know if you knew this or not, but there's basically three kinds of fundamental shapes of galaxies. There's really more because they divide it, but there's really three basic kinds of galaxies. Of course, there are spiral galaxies like our own. Then there are elliptical galaxies, and then finally there's what's called irregular galaxies. And as you might guess, the perfectly symmetrical spiral galaxy is the best suited for life precisely because it's the most stable over long periods of time. So if you can change to the next slide, Toshko, I have a picture of colliding galaxies, which does happen a lot. If someone would ask you, why do you need a stable galaxy for life? The answer is that there can be many events that are hostile to life when the structure of a galaxy is changing. So here's a picture that was taken by the Hubble Space Telescope, in which two galaxies are captured in the very act of a collision. Gravity is pulling them together, and so stars are crossing stars, and the result is much harmful radiation and other things bad for life. And if you could change the slide again, I have a slide of some irregular galaxies. What do irregular galaxies look like? Well, here's a slide of 4 different examples of an irregular galaxy. Well, if you're anything like me, these images stir my heart with the thought of the beauty and the creativity of God, but these are probably not galaxies that are conducive to life because they're too volatile. However, now take a look at our own galaxy so we can take note of why a perfectly symmetrical spiral galaxy like our own is a necessary condition for life. So if you can change the slide again. All right, so here is the Milky Way galaxy. Now, actually, it's impossible for us to take a picture, as you know, of the Milky Way galaxy because we're in it. So we don't really get a nice view of it like we do of other galaxies. But astronomers are working hard, even as we speak. They are working hard to map our own galaxy. And this picture actually is an artist's rendition of the Milky Way, but it's based on the latest data from astronomy. And so what you notice in this particular picture is that several inhospitable zones are identified. Life will not be able to exist in the galactic bulge. There's too much radiation in there. And certainly life will not do well in the black hole. Also, the molecular clouds and star-forming regions have harmful rays. But notice where our sun is located. That's us located in what we could call the safe zone. We're actually located between two of the spiral arms of our galaxy. We're not in the arms, we're between the arms. We're between the Sagittarius arm and the Perseus arm. So there's not so much traffic there. It's kind of like we would say it's a good neighborhood in which to raise your kids. There's not too much stuff happening there. So what we can say is that not only do you have to be in the right kind of galaxy, but you really have to be located in the right spot or the right zone of the galaxy. We just happen to be located in the perfect spot. Now, if you move closer to the center, what's going to happen is that there's more and more stars and more radiation. And if you move further out towards the far edges of the galaxy, there's not enough building blocks there to make a decent planet like the heavy metals that are needed for advanced life to exist. So scientists call this the habitable zone of the galaxy. So Toshiko, if you can switch to the next slide. That ring up at the top, you see that green ring. What you notice is that as you look at this diagram, is that most of the galaxy is not suitable for life. There's this one sort of Goldilocks zone where the star is located far enough out from the center of the galaxy so that supernovas are not exploding all the time. Remember I told you about that supernova that became 250 million times brighter than our sun? You don't want that happening right next to you. But yet we're also far enough away so that, so that rocky planets with the right composition can form. Now, not only must the star be located in the right place in the galaxy, but as you know, the planet must also be located the right distance from the star. So this is a different Goldilocks zone. And if you can change the slide again, here's now we're going to take a look at the habitable zone of our solar system. This is determined by scientists based on the fact that if you get any closer to the sun than this, then it's going to be too hot. Like Jay Richards was saying, all your water disappears. You're not going to have any life there. However, if you go too far away from the sun, then what happens? Well, it would be too cold, right? That's why Goldilocks wouldn't like that. It would be too cold. And if you're in the habitable zone, the temperature is just right. And what you notice is that, of course, Mercury is very close to the sun. So it's outside of the habitable zone. Venus, we notice, is a little further out, but still it's not in the zone. Earth, as you see, is located nicely within the boundaries, but Mars, when you get to Mars, it's too far away from the sun, and of course so are Jupiter and Saturn and the others. All right, so you get the picture. You have to be in the right place in the universe, and you have to be in just the right area of the solar system. But here is something else, and I'm just going to, this is the third one, and that's all I'm going to give you. You also have to be orbiting the right kind of star. All right. Now, do you remember last week I told you that Carl Sagan and other astronomers were so confident that intelligent life lived out there in space that they chose a certain star cluster called M13 and they beamed a message to them. Now, I don't know what the message was. Probably they said something like, send help, or come quick. But anyway, they chose the star cluster M13 because they figured, look, there's 250,000 stars in that cluster. And that way, not only would the odds be better, but probably the message would reach several different civilizations and various solar systems. So I have a slide of it. Toshiko, if you can switch to the next one, you can see that there's a bunch of stars there, about 250,000. The only problem is that star clusters are like the definition of hostile to life. Guillermo Gonzalez said that the odds that life exists there are virtually zero because a star cluster is so tightly packed with stars that it's impossible to have stable orbits around any of them because they're all, you know, like I told you, with the gravity, the gravity's messing with them. So the other stars mess it up. Plus, those stars are very old, and so the metal needed for the right kind of planet is not there. Now, in contrast, it's important to notice that our star is kind of special. Scientists figure that if we are going to find life out there in the universe, it's going to have to be around a star like ours. For a long time, people were saying that there's nothing special about our star, which is just a run-of-the-mill star. But now, even textbooks are starting to come out that point out that the sun is, scientists are finding out, is really somewhat unique after all. It's somewhat unusual. Our sun is a special kind of star. It's called a G2 spectral type main sequence yellow dwarf star. And what makes it special is that it is in the top 10% of the most massive stars in the galaxy. All right, so that's an important number. That tells you 1 out of 10, 10%. In fact, if you just pick a star at random, you're likely to pick one that is far less massive than the sun. Probably you would pick a red dwarf. Now, if you just do the math, immediately you can see that even with a conservative estimate, only 1 out of every 10 stars is large enough to be a suitable planet, suitable star for life. Now, why is that? Because if we were orbiting a smaller star, the habitable zone, as you can imagine, would have to be closer to the star if it was a smaller star than where it is now. And so the planet would have to be orbiting at a closer distance, which seems okay, but then the danger is something that is called tidal lock. And that's where the gravity of the star holds the planet in such a way that the planet always faces the star. It can't rotate like our planet does. It's kind of like what happened with the moon orbiting planet Earth. The moon got tidally locked, and so we only get to see one side of it, unless you go up there. Now, I am going to show you another short video here where, if you guys will just give me I need about 10 more minutes, if that's okay. If you do have to go, I understand, but let me just finish this up. So I'm going to show one more short video here where Jay Richards sort of summarizes what I just said about how you can see that the places where we expect to find life get increasingly small the more factors that you add. All right, so let's watch this video.
One example. One more brief example. I mentioned that we are in a galaxy called the Milky Way galaxy. And so if you are ever to go up in the mountains somewhere, in fact, Jonathan Witt and I are childhood friends, who's also a fellow Discovery here in Dallas, and he and I went to a camp for years in New Mexico as kids called Camp Blue Haven. It's over 7,000 feet above sea level. And so we were from Amarillo. And when I would always go to Camp Blue Haven at night, I would think there's always this weird misty cloud in the sky at night. I can't account for this. I thought it was so strange. And it wasn't until several years later when I was older that I found out, oh, actually, that's light from the Milky Way disk. What we're doing is we're looking edge on in toward the center of the Milky Way. And so we're looking through the kind of density of the gas and the dust and the stars in the Milky Way. And so if you get up in a really high elevation, you'll see that. That's why it's called the Milky Way. But the Milky Way is this flattened spiral disk of gas and dust and stars. And we're in it. We're one small member of that. And for a long time, astronomers just assumed, well, wherever you are in the galaxy, that will be fine. But in the last 20 or 30 years, astronomers have gotten much more impressed by the needs for the actual location. Even when you're in the right kind of galaxy, you need to be in the right galactic location, the so-called galactic habitable zone. Again, my co-author in 2001, before he was outed as an intelligent design proponent, I suppose, had co-authored a piece that was a cover story in Scientific American, not an ID publication, about the galactic habitable zone, and it's now a generally accepted idea. Is there going to be some places in the galaxy where you're just not going to want to look if you're trying to look for life? So here's the kind of basic story. Think of this as a bird's eye view of the Milky Way, if there were birds, out of the Milky Way. We're about midway between the center and the edge of the galaxy, between the Perseus and Sagittarius spiral arms. So about 27,000 light years from the center to the edge of the galaxy. Now that's actually the right place to be in. In fact, if we were in a radically different place, if we were in the inner part of the solar system or way on the outer part, we wouldn't be here. The reason is you get closer and closer to the center of the galaxy, there's probably a giant super black hole there. There are way too many stars. There's supernova going off. They're perturbing each other. Getting sucked up by a black hole, by the way, is lethal. If you didn't know that, you don't want this to happen. And so you don't want to be too close to the center of the galaxy. On the other hand, you want to be somewhat close to the center of the galaxy because that's where the heavy elements build up. And so you need things other than hydrogen and helium, one for a terrestrial planet and two for life. All right, and so if you get to the outer part of the solar system, it's astronomers call that metal poor, so not a lot of heavy elements. And so you want to be close enough to the center of the galaxy for there to be materials for planets and stuff like that, but not too close because of the kind of deadly stuff that's happening there in the neighborhood of the center part of the galaxy. So this is a technical diagram now that I've explained it to you in layman's terms. So you can see there's a kind of breakout here of our solar system, all right? And so then that's our sun, and then you notice the little kind of bluish green ring there. That's the circumstellar habitable zone, or the Goldilocks zone around our star. But then our star, our solar system itself, needs to be in a good neighborhood in the galaxy, about midway out between the center and the edge of the galaxy, between spiral arms, and rotating at about the same speed as the arms. Now, it's not surprising for me to tell you that's where we are, right? Because we wouldn't be here if that's not where we were. What's interesting is that it turns out that most of the places in the galaxy then aren't going to qualify. So even if we're looking for extraterrestrial life elsewhere, we're going to want to look nearby in the galaxy.
All right. So just to summarize the argument as we wrap it up today, I want to show you one more clip from the movie, The Privileged Planet. And this is the place where they really explain the argument for the existence of God based on the fine-tuning.
One example. One more brief example.
That's all right. So this is the place where they really explain the argument for the existence of God based on fine-tuning, where for there to be advanced life on a planet. And one thing to keep in mind is that this movie that I'm about to show you, I'm going to show you about 4 minutes of it, was made in the year 2004. So when one of the scientists says that the list of factors of the uniqueness about the Earth now stands at about 20. That's really outdated information. As you know, that number has drastically changed. If you remember from the class I told you last week, there's that article from Reasons to Believe, which identified 322 parameters. So the list is always growing the more that science learns. But nevertheless, this is a great summary of how the cumulative argument works. You already have it, but I just wanted to reinforce this. So it's about 4 minutes long. Take a look at this clip from The Privileged Planet.
If we find life out there, especially complex or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, that has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that it has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to the minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
Isn't that incredible? I love the way that it's presented there, because you can really understand how the cumulative argument works. It's a little bit of this and a little bit of that, but you have to have all of them, or life is not going to be there. So I hope this information has the same effect on you that it does on me. I mean, it stirs my heart to think of the fact that God created this vast, mighty universe, especially in order to create humankind in his image. That's the message that the Bible gives in no uncertain in terms. You know, for years people have said, well, that's just silly. You know, the universe is so big. Do you really think that God did all of this just for you, just for human beings? But the surprising thing is that as science continues to learn more and more about the universe, it's that rather than showing how unspecial Earth is, on the contrary, scientists in the last few decades are astounded with the way that everything seems to have been finely tuned just so that human beings could be here. So I am going to close this lecture with that thought, and I'll say just a quick prayer. But then, if you have any questions, we can talk for a second if you want to. But let's close with a prayer. Heavenly Father, we really want to thank you for the researchers and scientists who pour so much energy into learning about our universe, because it's exciting to us too, God. What we find is that you have made it possible for us to see with increasing detail the wonder of your creation. And God, we want to be people who are ready to engage with the culture around us, who want to say that it doesn't really point to God. And we want to be able to say, I really think it does. So Lord, empower us with the Holy Spirit that we might be able to engage the culture around us in sharing the good news that God, you are God, and you have sent your Son Jesus to us. In his precious name we pray, amen. Okay, so that will conclude this lecture. We can stop recording now, if we didn't already. And does